Welcome to this next lecture on acoustics. Last class we completed transverse waves on a string. We looked at several aspects. Today we will be looking at longitudinal waves on a rod that also has the same form of a wave equation. So, the topic is longitudinal waves in a rod or a bar. Some people call it a bar. Okay. So, there is this rod extending along the x axis. Okay. It has some cross section, circular, square, rectangular. However, these dimensions, these transverse dimensions are much smaller than this long dimension. Okay. And there is a wave initiated, there is a longitudinal wave initiated. Let's say it is forced in this fashion. So, okay, oscillatory manner, and so there will be now regions of compression. There will be regions of compression and there will be regions of rarefaction or expansion. Okay, these are rarefactions. And these are regions of compression. Okay. So, each particle as the wave moves will be oscillating back and forth about some mean position, and in doing so it will transmit this vibration to the neighboring particle, which will start doing the same thing, and it will connect with the neighboring particle, it will start doing the same thing. Okay. So, in the mean no particle moves away from its position, but about its mean position it oscillates back and forth, and that is how the wave will move. Okay. Now, since the wave moves horizontally towards the right, and because the particles oscillate along the direction in which the wave propagates, okay, so these are called longitudinal waves. Longitudinal waves, as opposed to transverse waves on the string. Transverse waves on the string. Okay. On the string, the direction of propagation was horizontal, but any particle would move up and down on the string. Okay. So, that is why these are called transverse waves. Now, just some basic assumptions here. The transverse dimensions of the rod are much smaller than the longitudinal dimension. So, let us say the longitudinal dimension is L and the breadth and height are B and H. So, what we are saying is B and h are much smaller than L. Okay. Now if we write our Hooke's law, we have epsilon xx is sigma xx over E minus mu by E sigma yy plus sigma zz. Okay. And similarly we have epsilon yy and epsilon zz, and we have gamma xy, gamma yz, gamma zx, etc. Okay. So right away there is no shear in the bar. There is no shear in the bar. That means there is no vertical any direction shear. Okay. So the corresponding taus are also 0, tau xy, tau yz, tau zx are all 0. Okay, so these are 0. So the corresponding shear stresses are 0, and the surfaces are unrestrained. Okay, so transverse dimensions are small. Transverse dimensions are small. Are smaller. Okay, this is what I mean. Okay, and free, the surfaces are free. The surfaces are free. Are free. Okay, as a result, what will happen is sigma yy we will take it as 0, sigma zz we will take it as 0, and so only epsilon yy, epsilon zz, epsilon xx and sigma xx will survive. Okay. So as the wave moves, where there are compressions, there is a bulge due to Poisson ratio, and where there is a rarefaction, there will be a necking. Okay, as the wave moves through the material. Okay. Now some people want to call this the quasi longitudinal wave. Longitudinal wave because of this Poisson effect, because of the Poisson effect. Which is due to the free surfaces. And small dimensions. Small transverse dimensions. Okay. So now what would be a pure longitudinal wave? If you have a huge amount of material like earth for example, and somewhere deep within, let us say there is a longitudinal wave propagating, then what would happen is that if in some localized region there is a longitudinal wave being transmitted, then if there is a compression, okay, there is a local compression, then there is a huge amount of earth material above it and below it. So this bulge is prevented, this Poisson related bulge is prevented. because this local wave cannot push that much material that is above. At the same time, if there is a rarefaction, this kind of necking also cannot happen because there is this huge material that has to be pulled in. Okay. So, now here the wave move purely axially with no transverse deformations. There epsilon yy and zz are also 0. So, some people would like to call this as the pure longitudinal wave. Pure longitudinal wave. One can understand that the material is stiffer in this case, and so the wave moves faster. Wave speed is faster. Okay, it is faster by an amount E over 1 minus mu square as compared to E in the quasi longitudinal wave in this case. Okay. So, we will be looking at this quote unquote quasi longitudinal wave. So, now let us see, we have a rod which is carrying a longitudinal wave, and let us say we are looking at a section, x is here, x plus delta x is here. So, I will separately cut this portion out and draw it a little bit exaggerated. So, I have x over here, x plus, let me call it dx is over here, and now there is a wave moving, there is a longitudinal wave moving through this. Okay. And let me say that the displacement, the symbol for displacement is xi. Okay. Xi is a function of x. So, now as the wave moves, let us say this face, this left face at x moves towards the right, and that movement is xi of x. It has moved by xi of x. Okay. And this face over here, it moves by xi of x plus a small amount which is del xi by del x into dx. Okay. So, del xi of x plus a certain amount delta, okay, and that delta up to first order is del xi del x dx. Okay. So, now let us see, if we list out the left side old coordinate, is x, okay. The right side old coordinate is x plus dx, and the left side new coordinate is x plus xi of x. Okay. So, this is x plus xi of x new coordinate, and the new coordinate of the right side is x plus dx plus xi of x plus del xi by del x dx. Okay, this is a Taylor expansion up till first order. Then we have new length. Okay, what is the new length of the element? New length of the element is the right hand coordinate minus left hand coordinate. So it is x plus dx plus xi of x plus del xi by del x dx minus x minus xi of x. So if we cancel x, we cancel xi of x, the new length is dx plus del xi by del x dx. Okay, and the old length was dx, so that the change in length is dx plus del xi by del x dx is a new length minus the old length is equal to del xi by del x dx. This is change in length. Okay, change in length divided by original. Okay, del xi by del x dx, change in length divided by original length is the strain. Okay, so this is the strain. So the strain is given by del xi by del x, which is epsilon xx. Okay, and the corresponding stress is given by E del xi by del x is equal to E epsilon xx. Okay, so if we take an element now and we exaggerate it, we have this element over here. I am showing it along with the cross section. Okay, so I have sigma xx plus delta sigma xx. I have sigma xx, and let's say this is x and this is x plus dx, and let's say the cross section is S. Okay, so the net force, so we are going to write the Newton's law or momentum balance for this element, which is sum of forces is equal to mass into acceleration. So the force on the left side is minus sigma xx into S. Okay, the cross section area is here also is S. The force on the left face here, I mean the right face here, is S times sigma xx plus delta sigma xs, increment from the face x. Okay, now that is equal to the mass of the element, which is density of the material cross section into dx is the mass, acceleration del 2 xi by del t square. So now if we expand the values at x plus dx about x, so we get minus sigma xxs plus s sigma xx at x equal to 0 plus del sigma by del x x equal to x equal to x, sorry, x equal to x into dx plus higher order terms which we ignore, that is equal to rho into s into dx del 2 xi by del t square. Now if we cancel off these terms, the first terms cancel off, and what we get, and ignore the higher order terms, the Taylor expansion, then I have s del sigma xx by del x dx is equal to rho s dx del 2 xi by del t square. Okay. So if we cancel out the s and I bring in this as my sigma xx, which is del by del x, sigma xx is given here. E epsilon xx dx. Okay, so dx also can be cancelled. We cancel dx also, is equal to rho del 2 xi by del t square, and now epsilon xx I replace by del xi del x. Okay, so I have del by del x e del xi by del x is equal to rho del 2 xi by del t square. Okay, I, for this simplest case, assume E is a constant and del xi del x takes on the derivative, so I get E times del 2 xi by del x square is equal to rho del 2 xi by del t square, and it turns out that E by rho has units of c square, square of the speed. Okay, so I get del 2 xi del x square is equal to 1 over c square del 2 xi by del t square. Okay, so this is exactly the same form as the transverse waves on a string. Okay, there are some parallels I just want to mention here, that when we derive the acoustic wave equation, we will dominantly use three equations. Okay, so one will be the continuity, two will be the momentum conservation, and the third will be the isentropic process equation. Okay, so here also there is a parallel. This equation corresponds to the continuity. Okay, this corresponds to the process, okay, and this corresponds to your momentum balance. Momentum balance. I just wanted to point out. So now we have this wave equation here for a quasi longitudinal wave on a rod, okay. Now we have seen many aspects of this form using the string, so I will just take a few examples and not too many, a few examples just to complete the idea, okay. So one is we will take an infinite rod as before, infinite rod, forced of course, and then we will take the finite rod, finite forced rod. So let us look at the forced infinite rod. So we have an infinite rod this rod moves off to infinity, and on the left I have a forcing, a horizontal forcing F tilde in the form of capital F e to the power j omega t. And so there will be regions of compression and there will be regions of expansion or rarefaction as the disturbance moves, okay. Now because the form of the wave equation is the same, right, no mystery that one by c square, let me put a delta to indicate it could be complex as before, t square, and the solution we know already, the general solution is of this form, a tilde e to the power of minus j k x plus b tilde e to the power of j k x e to the power of j omega t. Now again the rod being infinite, rod is infinite, and therefore when we initiate a disturbance here at the left end at x equal to 0, okay, let me correct it, people would like to call this semi infinite, okay, let me correct it, semi infinite. So x equal to 0 is here and it extends to infinity, we will call that a semi infinite rod, not an infinite rod. So if it is infinite, it will be infinite in the other direction also, so that is not the case. So we will call it a semi infinite rod, okay. So here, so this is now semi infinite, rod is semi infinite. And so if we initiate a disturbance over here, it starts to move and it continues forever. There is no point where there is a end or a discontinuity for a returning wave, So this equal to 0. So this B, which is a left travelling wave, is 0 because there is no source towards the right. The source is at x equal to 0, there is no other source, and therefore there cannot be a returning wave, okay. So B tilde goes to 0, so only A tilde survives. So now there is only one unknown, which is A tilde, okay, and therefore we need one boundary condition. Okay. So, we will look at this boundary condition in the next class and find a solution to this problem. Thank you.